Let us start the third, last, but at no way least, lecture for this series on a historical perspective of distributed computing. Our two speakers today are Frédéric Hemmer and Les Robertson. Frederick studied electrical and mechanical engineering and computing in Brussels. He joined CERN in 1984, where he served as system engineer in databases, real-time systems, and more generally distributed computing. Between 1990 and 2005, he fulfilled various roles, including system software development, computer operations, and line management, and participated in various e-infrastructures related to European Commission projects. He led the CERN IT department between 2009 and mid-2021, and he is now a member of the online team of the LHCb collaboration, and also a member of the Swiss Innovation Agency Council, INO Suisse, and member of the IEEE and ACM. Les worked on operating systems development in the United Kingdom before arriving to CERN in 1974 as a systems programmer for the CDC 7600 computer. He spent 36 years in data processing at CERN in various technical and managerial roles, ending his career as the leader of the LHC Computing Grid project. So now first we welcome Frederick, who will speak about the Shift project, and then Les with the grid. I shall mute now, and Frederick, please unmute yourself. You are still muted, yes. You are still muted.
Can you hear me now?
Yes, perfect.
Sorry,
yes.
I tried to fiddle with the system that was not very clever of me.
No problem.
And no, I cannot change my slides. So can you see them?
This is perfect. It is the cover slide. Exactly the entry point. Very good.
Okay, so I'm not starting with less presentation. That's already very good. So, so a few acknowledgements. I'm speaking about Shift, but actually this is the work of many, many people over years. I've tried to put a few names of those that I remembered, but I certainly forgot a lot of them. The other thing to show you that we are really back in history, and Maria, thank you for having clarified the century in which I joined CERN, in case there was any doubt, in 1984. It's a long time. So I've tried actually to reuse all slides that were produced at that time. You will see that, well, PowerPoint was not necessarily super professional tool, or at least the one making the slide, which is in most of the cases myself. I had a few surprises when doing that, and one of them is related to what we were talking about yesterday, data preservation. How do you access all data? So this is a surprise I had while opening one of these old files, that 1997 presentation could not be opened anymore because the format is not supported, despite using only tools from Microsoft. So I think this is interesting. Briefly, I will try to look a little bit backwards at what the computing landscape for physics was looking at that time, talking about the whole CSF and Shift project. And I think very important related to that, the birth of PCs as a physics processing platform. The young people only know about PC servers these days and x86 architectures. So a few images. And some of them are very important. So we were using tapes. You see that on the left. actually, I will go to the next slide. This is a view of the computer center. And it's very interesting. At the front, you've got CDCs, I believe. I don't know what model. Les will be able to tell. At the back, you see blue stuff. Yes, this is IBM. I think it was a 3081 at the time. But in the center is tapes. So we had tapes inside the computer center. And this is the area that we have occupied afterwards. On the previous slide, there was also the Cray, which is very important in our story. Because that's actually a supercomputer, but supercomputer that was running Unicos, a version of Unix, and that made a fantastic difference. You will see. So tapes, as I said, we were using that. These were 200 megabyte tapes each, and they were mounted not by automated libraries, but by human beings, 24/7. So CERN computing service in those times, in the 70s, mentioned already CDCs and IBM mainframe for general purpose services, batch and tapes. In the 80s, mini computers start to arrive, VAX 780s for interactive service or special purpose service such as database and CAD/CAM, or Oracle service was running on that. And what's also very interesting, Ben and Maya talk about that yesterday and the day before, the rapid growth of internal and external networking, and the first Unix service and Apollo workstation in 1982. Then in the second half of the 80s, again, IBM mainframe, VAX computers, plus the Cray that arrived, and a growing disconfiguration, and then the absolutely explosion of networking everywhere, and the small workstation as well arrived. And in 1988, Lab Accelerator begins operation, and actually workstation clusters were used for data reconstruction at the experiments, replacing custom-built processor, which were IBM emulator, and a really growing number of private clusters running on VAX VMS for data analysis. But still, the IBM mainframe remained the principal provider of batch and tape, and also interactive services. Then arrival of reduced instruction set computers, which offered a power absolutely comparable with mainframe, and sometimes even more, for high energy physics code at a much better price performance. And what we didn't expect immediately at the beginning is the arrival of much cheaper disks, SCSI disks. So workstation look attractive as a platform for some services, and that's what we've tried to do. And you see here, I think it's interesting to look at that from 2 points of view. First of all, this is an illustration of less talents for making these kind of PowerPoint presentation and using all sorts of graphic objects that I couldn't do, but also the data rates here. They are not very big compared to today's. You see 100 kilobyte per second to tape, talking about 2 megabyte per second. This is almost nothing, but that was what was happening around the beginning of the 90s. So in terms of history of what I will be talking about, 3 projects, but related to that, and as a direct consequence, is that our Cray supercomputer was decommissioned in 1992, and the IBM mainframe disappeared in 1996. That was not easy for some people. That was real paradigm shift for them, and some of them would never be able to adapt to the changes. First project is HOPE. HOPE actually is a joint project with Hewlett-Packard, and they provided us with a machine called the Apollo DN10000. They were just acquiring Apollo, which came with 4 processors and offering a very powerful system for at least simulation. And we installed on that the NQS batch system, exactly the same one as on the Cray, so it was relatively easy from a user point of view, and connected to storage tech tape drive, not the one you know from 5-10 years ago, but still tape drives, IBM 3480 compatible tape drives. And the main usage was for simulation. Quick limitations were rapidly seen, network performance and tape support, but they provided a very good service for the price we paid, especially if it is HP giving us this equipment. They also provided somebody to work on that, Eric Jägel in particular. Then we started to change a little bit and created the central simulation facility, based this time on Hewlett-Packard workstation, smaller ones, because the Apollo line was actually stopped, but they were very low cost. And as you can see in the numbers here, the service grew from 16 to 45 machines, and the second generation actually used less powerful machine, but with a much better price performance. And this is what it looked like, interconnected by Ethernet, because the simulation doesn't require a lot of data, and with an interface to tape servers. But rapidly, CSF became the principal provider of CPU cycle in the computer center in 1992. Then Shift. That was designed in 1990. We started to work on that. The idea was to provide not only CPU cycles, but also fast access to large amount of data. And as I hinted in the previous slide, good tape support. Of course, cheap, easy to expand, and vendor independent. At the time, there were many vendors of workstation, and actually many different CPU architecture as well. The first implementation of that was in January 1991. However, one of the things we should remember is that before putting this service in place, we had to understand all the networking issues, the networking performance, the disk performance, these kind of things. A large number of studies were made. And I cannot resist in putting an extract of the source code of one of these programs called Jensen. It was just to measure how fast you could transfer two machines. And the author is somebody called Les Robertson, who is actually in this meeting. And he was a manager. So you can imagine that I was surprised that the manager could program, not only program C, but doing network programming with January 1990. And this code was actually modified by a certain Ben Siegel, which is also here. And I left the spelling mistake in the comment that he included on options. The model was very simple. You have, let's say, a high-speed network. You put CPU servers, these servers with a disk, and you attach to tape, and you transfer, you do your analysis by transfer the data to this. Well, that you need a high-speed network. And I'll come in a second for that, because it is, I think, very important. A few design choices were made. Unix, which was not necessarily something that everybody appreciated. We were, remember, mainframe, Pax VMS. So not a lot of people did Unix, except on the Cray. System-wide batch jobs, in order to give a single system image to the whole system. And very important, the target was to have style of service. That is something running 24/7 of the style of the Cray, which was a very nice service. Also, the idea being to have a pseudo distributed file system and with very little file sharing, which makes the thing much simpler. And using tapes with very simple primitives, copy disk to tape, this file to tape, copy file back if you need to read it. And so it worked somewhat. This is what it looked like in 1992. Again, I think the authorship of this is less. We started with silicon graphics equipment here, and with 250 gigabytes, not petabytes, gigabyte of disk. and you see the CSF that I mentioned, the Hope. Our best tape server was still the Cray at the time, expensive tape servers, but very effective, and nascent service based on STK4280, which was providing 3480 compatible drives. And I spoke about the backbone, network backbone. So this is the Ultranet equipment that we were using, proprietary, but which offered, remember, 1992 gigabit per second capabilities, and was key to enable all this transfer going on. Then at the back, you see the first machine we embarked on the project together with the Opal experiment. And at the back were the disk shells, and the disk shells were not bought from main manufacturers. We were actually buying that mostly in California, where they were assembled in some ad hoc racks, and we were trying to interconnect. Maybe there will be opportunity later on to talk about that, but this caused actually a lot of problems because we didn't realize that the distance between the machines and the disk was bigger than the normal single-ended SCSI connection would permit, and would give all sorts of I/O errors. And you see myself here. I've changed quite a lot, as you can see, and Gordon Lee, who was operating all the machines. Just a mention of Ultranet, because that was something absolutely unique there, and especially the bottom part. So the transport layer, up to the transport layer, this was done in hardware. Ironically, and related to the talks the two previous days, the first version of the Ultranet hardware was running TP4. So one of the OSI, the false OSI layer. They realized later on that maybe this was a mistake and was changed to TCP/IP, but not immediately. So they had compatibility libraries for TCP/IP. And so this gives you an idea of the transfer we were able to get at that time from one machine to another one. So the individual transfer at only 12 megabytes per second, but that was actually pretty fast, and certainly much faster what the disk could deliver. Then the whole thing, of course, I was saying about a single system image, but that can only be done by adding a little bit of software. And you see here the various components of it, a Unix tape subsystem. So we were initially using the Cray, but then we wrote our own to be able to handle the tapes. Unix and tape is not very compatible. If you look at the tape driver on Unix, it's probably the most simple entity that you can find, essentially only meant at doing backups, nothing else. This is not how we use tapes in high energy physics. A key component was remote file access, and this was done because the current protocols, the protocols at that time were not fast enough for achieving the performance we wanted, and we wrote ad hoc and targeted performance optimization on this layer. Remote tape copy system, a disk pool manager, which was not very successful in order to allocate disk file for people. And all that thing was replaced later on by what we call the tape stager, which was much more effective. NQS I mentioned, and very important integration with, I was writing at that time, standard I/O package. I meant their standard I/O package for high energy physics data handling. And very important, it's not enough to have systems and IDs and things like this. You need to provide the service. So little by little, we grew this service, put the network operation in, monitoring, and many other things, of course, so that it could be a reliable service running 24/7. Mentioned RFIO, the remote file access system. CIO compatibility library interface to Fortran and optimized for specific network, in particular for Ultranet, but also was mentioning many different vendors at that time, and all these vendors were showing different behavior in terms of networking, especially when interfaced to special systems like Ultranet. And the tape stager, this is how it goes. You want to have a tape, it goes to the stage control, will schedule on a tape server, copy it to tape, a copy from tape to disk using RFIO, and here it is. You've got your file, you can work on it. A bit later on, this is how the service look like. Again, I think all the credits are to be given to Les. Actually, his name is there, so that's very good. Growing, you see 24 silicon graphics, even interface to a special parallel computer called Mako CS2, and many other things. Later on, September 1994, you see all the equipment, but what's more important here is that you see all 4 lab experiments finally embark on using this system. At that time also, we introduced the idea, it's nothing revolutionary, but important, of central data recording. In the past, the experiments were used to record data at the experiments and bring this data using data by bicycle or cars or trucks and things like this. Now, with the improvement in networking and with this layer software that we wrote, it became possible of directly recording all the data directly on central facilities. And this is an extract of 1995 talk to the experiments with a few advices here. Plan this space 6 months in advance, at least in the pit and in the disk pool, and plan network bandwidth over years. This is still true now. Actually, I would say, especially these days, plan your disk space 2 years in advance, and same for the network. Writing tapes, please use large blocks. Don't use small files. It says 200 megabytes here. Still true today, except that the small files would today be 1 gigabyte or 1 terabyte or even more. And block size is very important. Do not delete the file at the pit before successfully written to tape. Still true today. Keep a buffer large enough to cover for failures. Still true today. 4 days, that's around Easter, where some people had 4 days holidays. So that was planned well in advance, things like this. But the interesting thing here is not this one. The interesting thing is VMS support is weak. Yes, we did port part of the software onto VMS because of this large cluster of workstation available in the experiment. An idea of the type of different disks at that time, a lot of variety. Remember, again, in terms of disk drives, it's like computer manufacturers. There were many manufacturers of disks, but a large variety. This is how Shift looked like in 1997. You see silicon graphics here, a few digital equipment machine there, a lot of HPs there, very few Suns, but there were some. And 1 year later, about the same, except that a few silicon graphics disappeared on the right. These were the Challenge series, replaced by 2 Origins, and essentially that has been the end of the expansion of Shift, because at the same time the PCs started to play a role. What we did with the PC is very, very similar. So first platform for simulation, PCSF, PC-based central simulation facilities. And we started with dual Pentium Pro at 200 megahertz. Yes, we were not talking about the gigahertz at the time. But 200 megahertz was just enough to start to be interesting for doing physics processing. It was much slower than the silicon graphics we had. The funny thing is that this was not on Unix. The first PC-based facilities that we operated was on Windows NT. And it was very stable. I'll give you a screenshot of that. The first sort of 810 machine there, at least 10, and in 1988 it grew. And yes, these are Tor-based machine. The racks, some rack-mounted model existed, but were by far too expensive. Okay, and the principle is exactly the same. At the back end, you had servers which were not the Cray anymore, but just Unix tape and these servers, the network, and all the client interface to Windows NT. If you don't believe me, these are the queues and the Windows monitoring going on. Now, something important arrived. But at that time, just a bit later, is that Linux arrived. And of course, it was much easier for physicists to use something like Linux compared to Unix than Windows NT. And that really has been the start. So the Nomad experiment were the first one using a central facility in 1997, towards the end of the year, with Pentium 2 at 206 MHz. Okay, then a few lessons at that time. So I don't know how I'm doing on time. Yeah, that's probably okay.
Let me unmute. I think you are perfectly okay so far. You have been speaking for 30 minutes. Maybe
yeah, it's finished soon. Okay. So these are sort of lessons that I wrote in 1996, that things change fast in terms of CPU, disk, and technology change. Yeah, well, this is still true today. Network is the core, still today. I said it's complicated. Yes, it is complicated, especially with high-speed networking. Ironically, the job I'm having now has to deal with network, disks, and transfer at 16 or 18 gigabytes per second, a bit more than at that time. But the problems are very, very similar in nature today, just faster. Something that maybe we didn't appreciate at the beginning is that this is actually quite a lot of equipment that we had there. But as usual in scientific centers, the manpower is not increasing. We had a lot of diversity. So this started to be really an effort when you have to manage hundreds of systems, dozens of these. My own conclusion at the time is that probably we were too distributed. The things that were going well were people having quite large machine closely interconnected. So we start to pay the price in terms of system management. So of course, we put a lot of effort in trying to centralize things, to automate, to clone. We were looking at multi-vendor solution for doing this. Some of them were existing, but were very, very, very expensive. I will say no name at this point in time. And 1996, major challenge arrived. Yes, LHC, we were starting to talk about LHC. And look how naive we were. This is what was anticipated to be a typical proton-proton experiment, scheduled at that time to be started in 2005. And we said, yeah, that's very important. It's 200 times what we have in terms of requirement. But look at the numbers. Raw data, 1 petabyte per year. I think the Sun Compute Center has now of the order of 350 petabytes. So the LHC has produced much, much more data than anticipated or promised. I'm sure we will come back on that in this talk. Yeah. So this reaching a little bit the end, the few considerations here. So I don't think we've created new technologies, but we've rather acted as integrator of new technologies that were coming on the computing market, but also leaving. Many of the companies that I've been mentioning are not existing these days anymore. We've been using de facto standards. De facto is important, that these are the ones that are used by other people, where you can share experience and utilize your efforts. We've benefited a lot of improvement of new networking solutions. I had no time to really speak about that, but Ultranet was replaced by HP, by many other things. And very important, we have been driven by the needs of physics. It was not just for fun, not a computer science exercise. It was driven by the needs of physics, and their needs is increasing every day. I think we have been also very lucky to be inspired and guided by people such as Les and Ben. We've been lucky in benefiting from budgets from the IT department, which was not called the IT department, but computing and networks. Lucky is not the right word. I think in part Les has been key in trying to convince a few millions to be diverted to non-mainframe thing. We've been lucky to have been constantly pushed by the appetite of the experimental physicists for data and also for processing the data. I think one big lesson is essentially to work with them from the beginning and not to sort of create a system and says, they have a wonderful system that will solve all your problems. What is your problem? No, from the beginning, you have to embark them on that, and it's usually a win-win situation. I think many lessons and conclusions from that period are still valid today. Numbers have changed slightly by 3 or 4 orders of magnitudes, but the number of people or the budget have not increased that much. So we have to innovate a little bit, to be opportunistic in our choice, and to believe that it is possible. Thank you very much. I think this is the end. I've given you a few references in case you want to look at that.
Thank you very much, Frederick. Would we agree that we go through to Les, or would people like to discuss questions right now for Frederick? I think maybe a free format discussion at the end across presentations would be more relaxed. So why don't we go forward to Les, if you would like to share screen, Les, and then we have more time for global discussion.
Perfect. Okay, can you see that now?
Sound and screen share perfect. Thank you so much.
Okay, so yeah, so I'm going to talk about the early history of the computing grid for LHC. So this is from the beginning, the conception of this, to run 1. So run 1 was in the end, started really end of 2009, 2010, because of the unfortunate accident in 2008. But throughout the early part of this project, we were aiming first at a 2005 startup, then 2007, and then 2008. So I stopped in 2008 because that was the point at which we were ready. So I say that this is a distributed project to build a distributed data grid. And this is really a collaboration of the LHC community. This is not CERN activity. I mean, CERN is where the LHC is, but the importance of this activity was done by the LHC community. Okay, just to put the talk in context, Frederick showed you a few things about the computing center about 10 years before this. In 1998, older people here will remember that year very well because it was the year that Bill Clinton was impeached over his affair with Monica. But it was also the year that Google was launched in September that year. The best mobile phone that you could get was the Nokia 6110, 9 years before the iPhone appeared. If you had a good home network connection, that would be at 64 kilobits a second, and an inter-site network was 622 megabits a second if you could find it. Okay, a big hard disk of the type that Frederick was talking about, or at least a disk of the size he was talking about in 1998 would hold 12 gigabytes in a 5.25-inch package, and the tape cartridge held 20 gigabytes. Now, I think that the Apple Watch version 7 has 32 gigabytes, I think, inside it. So we've moved a lot forward, but you have to, when I'm showing you this, you have to think about how big these numbers seemed at the time and how small they seem today. Okay, Amazon had been selling books for 3 years, but it would be a further 8 years before they opened what was probably the first cloud service, the Simple Storage 2 and Elastic Computing 2 services. Now, the situation in HEP computing was that PC clusters with Linux were the standard, which is seen from Frederick's talk. Remote job submission by the internet. So to some extent, high physics were working with sort of private clouds, with big computing clusters, and everybody connected to them by the internet. Major sites had lots of experience of mass storage management systems with tape staging, cache management, and automated robots. And we had very good TCP/IP network interface, expertise for efficient and reliable data access. Now, in LHC, from the machine point of view, construction had been approved in 1995. And the target at that time, in 1998, the target was still 2005. The 4 experiment collaborations had already prepared initial estimates of the data rates and storage requirements that they would require. And this was the big problem. I'm just trying to get rid of something from my screen. Can't get rid of it. Okay. So the big problem was the amount of disk, CPU, and mass storage which people required. Now, if you look at what these numbers are, especially the CPUs, who knows what a million spec-int 12s are today? But the point is that if you look at the yellow line on the top right-hand graph, the yellow line is what CERN's computing budget, which at that time was providing the computing for the LEP experiments, what the CERN computing budget would be able to install as you went through using a sort of Moore's Law's extrapolation. Now, for people who don't remember the Moore's Law, this was basically that the number of transistors in a chip will be multiplied by 2 every 2 years, and the cost of the chip will be halved. So using that, which was actually quite a good extrapolation at the time, you can see that CERN would actually not be able to support very much of the capacity needed to do the processing for LHC. The situation with disks and mass storage were probably a bit difficult. In the case of mass storage, CERN would have to provide about 1/3 of the capacity. But the main problem was that you would have to look for the budget for these resources. You'd have to look outside of CERN, which meant basically that the experiments would have to go back to their funding agencies and convince them to provide more money after building the detectors, to find more money to set up computing facilities. Now, the belief was, and I think it was absolutely the certainty was that this money would not be placed at CERN. So most of the computing capacity that we use would have to come from outside. Okay, so search for a solution. So this started already in 1997 with the Monarch Project. And this project was chaired by Harvey Newman from Caltech. And the idea, the aim of the project was to assess the requirements, technologies, costs for LHC computing, to propose a solution within the constraints of the large data volumes, the need to incorporate resources spread across the world with a wide range of capacities and functionality. The bandwidth of the wide area networking that you could expect to be available in 2005, and using an architecture and technology that was convincingly feasible to be implemented in the time available. Now, the Monarch Project, the important thing about it is that Harvey had put together a large set of people to study and work on this. And this, he had put together a set of people who were drawn from a very, very broad area of backgrounds, expertise, right across the LHC community. And this was very important because by the time that the final report was produced, there was a general agreement on how you should proceed. And the general agreement included that the grid concept was probably the best underlying technology to be used. Now this was, there was a bit high risk here because this was early days for grids. Most people only heard about grids from the grid blueprint, which was published in 1998. Carl Kesselman and Ian Foster, two computer scientists from the United States, had been working on this, but they'd been working mainly considering the needs of high performance computing sites. They had, however, developed through a project they were running, the Globos project, they developed an open source toolkit that included the basic functions you needed to operate a grid. And there were a few early high energy physics pilots which had started. There was a significant one in the US, the particle physics data grid. At INFN, in INFN in Italy, they set up a distributed simulation facility, and there were a number of activities within HEP spread around Europe and elsewhere, which were looking at trying to use this grid, seeing how you could use this grid technology to manage a widely distributed service. So this, however, gave us some confidence. These pilots gave us some confidence that we would be feasible to do this on the time scale. The model that Monarch came up with was a sort of a multi-tier model. I mean, it's on its side here, so you don't really understand why it was called tiers. It was originally rotated 90 degrees anti-clockwise. So the top tier would be CERN with a copy probably of all the data. It would certainly have a copy of all the data. And you'd have a mirror of this in the United States because networking, remember, was pretty limited at that time. And you'll see here that they even put in an optional air freight connection between CERN and Fermilab, which would at that time probably have produced rather higher bandwidth with a large latency, but rather higher bandwidth than the X22 megabit a second link, which we thought would be available. Anyway, so the idea was that these tiers were organized by the functionality and the capabilities of the computing, the centers which would be involved. So at the top, you'd have the CERN and maybe a mirror, which would it would be responsible for storing a copy of everything, archiving it, and all the rest of it. It would have capacity to do the initial reconstruction. Then you would have a series of what were called here tier 2 centers, which would be large computing centers distributed around the main countries that were involved, which would also have a good mass storage capability. And they would serve the data to the next tier, which would be smaller regional centers, maybe in universities, maybe in labs, and where the analysis would be done. And the simulation would probably be done there as well. Now, as this was going on, the idea of using the grid caught on. And so initially, this was thought of as a rather structured environment. But by the end of Monarch, it was realized that you don't need this structuring, because if you're running a grid, then basically all sites have the same functionality. It's just that they don't provide the same services. They don't provide the same capacity, or they don't have the same data. But you don't have to structure this rigidly in this hierarchical way. So the structuring now is more in terms of the service that you would provide. So the service is what basically for CERN as the tier 0, the tier 1s would be these big computer centers, which also have robotic capacity for mass storage. And then the tier 2s would be the regional centers, which are mainly computation and sufficient disk space to cache the data that's being used. So there was a big move because of this grid concept. We had this move from it being a sort of hierarchically structured environment to one in which you get the grid components installed everywhere, and the experiment then can decide which of these resources it's going to use. Now, in 2000, just at the time that the final report of Monarch was being produced, there was a computing and high-energy physics meeting in Padova. And a large amount of the discussion there was about LHC computing using a grid. And it was basically just agreed there. It was a bit of a surprise that there was no, I don't remember anybody actually arguing or even, proposing anything else. So we had basically ended up after this meeting with an informal agreement, but everybody was basically, it was a consensus that this is the way to go. So I must say that Monarch really had done a very good job, and Harvey Newman deserves a lot of thanks for organizing it this way and producing his report. I should say also that Monarch, they had done a lot of simulation on what it would really, and what you could actually do with the bandwidth that was available. So there was really good reasons to think that this was something you could do, provided you could get the software going. So how do we build this? Well, we had lots of experiences, as Frederick explained. We have lots of experience with the components of the nodes of the grid, large and small clusters, mass storage management, wide area networking. We had a starter set of grid components to get off the ground, but these were not really designed to handle the volume of data and the inter-site file transfer performance that we would need, nor had they been tested out on the large number of nodes. We ended up, by the time LHC started, we had 140 nodes in operation. And when we had thousands of users, and at the analysis level, completely unpredictable patterns, just depending on what topic was currently becoming interesting for the physicists. Now, there was informal agreement to go ahead. Everybody basically agreed on it, but this was going to be very expensive in money and manpower. And so we needed a formal structure that was acceptable to the CERN Council and to the agencies who were funding the experiments. And so this formal project was set up in 2001 to coordinate the planning, provisioning of the computing centers, to enable institutes and funding agencies to pledge resources and manpower. So all the institutes would sign memoranda of understanding, and each year would pledge their assets in the way that they do for the high-energy physics experiments. And then the project would provide a collaboration style structure to ensure the wide representation of all the stakeholders. And this is something absolutely essential, because we were working with new ideas which were still developing. And so you needed something where you needed a structure in which you could arrive at consensus and decide which of the many, many options that you would choose to go ahead with. Then this project reported to the LHCc, the LHC committee, which is the high-level coordinating body for experiments using LHC. It was at the time, it still is. Okay, so developing the middleware. Why it was called middleware, I'm not sure. It was basically the software to run the grid. It was middleware probably because it was in the middle of the grid. But anyway, the idea of the grid had stimulated many, many R&D projects. I only have a small selection of their logos on the right-hand side here. Many of these projects, and most I think, had HEP participation. These are concerned with developing the middleware from the basics that the Globus project had provided, and operating test beds. This was excellent, lots of different ideas, highly motivated developers. The difficulty is that there were so many of these projects. On the one hand, so much was coming out, lots of it was completely novel. And we would have to use, we would have to decide which of these we'd use, what's the best choice to make from all these different possibilities. And we would need to have long-term support for the components, but these R&D projects had 1 year, 2 years, 3 year, perhaps lifetimes. So that was a big issue of how to go from this large number of projects and converge on something which LHC could use, and the community would have to take it over and support it in the longer term. However, LHC planning was evolving, and the planning for the machine was evolving, and the startup date had now slipped to 2007. So we had a breathing space for development before we'd have to fix the interfaces. Now, the projects that we were working with here, they all, since there was so much HEP involvement in them, they were all aware of the fact that you can't just go ahead with large numbers of different varieties of middleware. And things started to converge on both sides of the Atlantic. Well, it was in the US rather than in the rest of the world, because in Europe, the EU data grid funded, the EU funded data grid project was actually led by Fabrizio Gagliardi from CERN, and it included many HEP institutes, and the follow-on project, EGE, which was also led by Fabrizio. With that, it was agreed with the EU that institutes who are taking part in LHC could be associated with the project no matter what their home country. So eventually we had 34 countries who were using the EGE software and infrastructure. Now in the US, LHC participants all migrated towards the open science grid. And so as the LHC beams grew closer, we really only had these two base sets of grid middleware, which we had to in some way put together. So the way it was put together was we agreed that there would be a set of baseline services which would be provided by all of the grid nodes. So this is a list of the services that were in the baseline definition. Then in some cases there were more than one for various reasons. In some cases there was only one choice. But it was very important to keep this converged, because there's so much work which the experiments have to do on top of the grid. So you have the grid, which is advertising its resources, which is providing capabilities for you to launch your work, to move your files around, to catalog them, etc., etc. But from the experiments point of view, they have to find where the resources are, and they've got to decide where to put their data. And to do this, you have a lot of experiment software. So I give here the example of the Ganga system, which was being developed then, which was used by Atlas and LHCb as the grid interface. So this was to provide a single interface for Atlas LHCb physicists for all of the grid-based work, including analysis, including Monte Carlo productions. So the idea was that this would enable you to switch easily between grids and local running. So you would test your program locally, and then you could just switch the same job to the grid. It included backends for LCG or EGE, which was what the LCG was largely then using the G-Lite software from EGE. Now Frederick was the coordinator, the manager, I would say, of the EGE activity, the middleware activity, and then the open science grid in the US. And then there was an outlier, NorduGrid, which for whatever reason was not involved, was not integrated into EGE. Okay, so, oops, what has happened? Okay. Okay, this is just an exploration of what the Ganga software, they had the, what to run, where to run, what to do with where to find the input data, where to put the output data, how to split up your job, dividing it into sub-jobs of a reasonable size to submit to the grid, how to submit it, where to submit it on the grid, and how to combine the outputs when the job's finished. So this is a lot of software, and this is one of the reasons why it was important reasonably early on for the grid software to be standardized or to be defined. Okay, so now the first service, this is going back a bit now, the first service opened in September 2003 using two grids, the European data grid and the OSG, which was at that time not yet called OSG, but it would use the virtual data toolkit. There were basic agreements on principals registration, how the security would work, certification, how the distribution process would go about. There was a grid operations center in the UK. There was a call center in Germany. So we had all the basic components needed for running a service. And in July of 2003, this was deployed to the 13 initial centers, which went live in September. And then it ramped up towards the end of the year, so that by the beginning of 2004, we had a service running. Now this then went through various versions before we reached 2008, the startup date. And as this was going on, we ran several service challenges in order to test out the progress and the usability and etc. of the service. So these the first challenge, service challenge in 2004, and then we had another 3 before we get to the final readiness challenge in 2008. So the focus here is in sort of real production usage of the service over weeks and for weeks on end, testing all the various components, and providing a service which would be usable by the experiments for the data challenges which they were running in parallel. So we would put up a new version of the service, we would test it out with the service challenge, and then the experiments could use it for their data challenges. So how did this work? So the first data taking was in 2008. Unfortunately, for a very short period before the quench accident happened and postponed everything for a further year. But you see, as we were ramping up, this is the number of jobs per month that's shown here. So we were ramping it up to September when the machine was opening. Things stalled then, but actually the work level was maintained for the year until the accelerator started up again on the real run one in the end of 2009. And within 6 months, we'd arrived at 1 million jobs a day, which was the target. So that's one measure of how it was going. Now I come back now to the resources. So here I've split the resources by CERN, the tier 1s, these are the big computer centers, and the tier 2s, the large number of smaller ones. So for disk and CPU, CERN is a relatively small player here. I mean, so CERN was providing in the end 16% of the CPU available. So most of this had to come from the grid. So if the grid doesn't work, it wouldn't work. Okay, disk, is spread out to the area, to the places where the analysis is being done, and is only in the mass storage area where CERN becomes a 1/3 operator. as it has to maintain a copy of everything. So you can see from this that the grid had to work, or we'd be in difficulty. Now here's your counting from July 2010. So this is like 6 months after Run 1 started. So on the left, on the top left here, it's split by tier. So the big light blue area on the left is the tier 2 centers, which are exploded down on the right here. So you see that the top, the rest of this, about 45, 50% perhaps, is the CPU, which was delivered by CERN in the tier 1s, with CERN at the top here providing a relatively small part of this. But then on the right, you see CPU delivered by country. So it's not actually by institute, but by country. But you see that there's even the very small contributions here were all, were all being used and taking part in the service. Now, the interesting thing is that CERN wasn't heavily used. I mean, it was probably only at this point about 50% used. Now, the big fear was that everybody would just jump on CERN because at startup, many of the physicists would be there anyway, looking after their detectors. And, the old system was you just submitted your job to CERN. So there was a fear that that's the way it would go. But actually, the grid was working well enough. And importantly, the experiment interfaces to the grid were working well enough that already 6 months into data taking, they were able to use the capacity that was there. Okay, the other big issue was, which was concerning us very much at the beginning and in the Monarch period, was whether the network would be strong enough. Now, by the time we actually started, instead of a 622 megabit connection, we actually had a dedicated 10 gigabit links between CERN and all of the tier 1 centers. And there were many additional links between tier 1 centers. So we had this 10 gigabit dedicated private network at the center of the grid. Everyone else was using just the research networks that are available, but this was much, much better than we could have anticipated in 1998. So we did very, very well from the networking point of view. And I believe today that it works so well that experiments really can just submit a job and copy the data from wherever it is to wherever they're running. So that's all I was going to say. A few comments. The worldwide LHC computing grid was set on the right track by the Monarch Project as a community-wide endeavor and aimed at exploiting what at that time was a novel type of distributed service. There was close collaboration with and funding from the EU and NSF and many, many national grid middleware projects. So that was very, very, we were very lucky, and it wasn't just luck because there were many people who were involved in making these collaborations. So the funding agencies worked well with us. The significant and continuing contribution of the regional centers enables large and small centers all to have a stake in the service. The service challenges and data challenges were, absolutely essential to show everyone what was happening and to encourage people to, work on their software, and also enable us to see what the components that were really working were and which components would have to be dropped and which components would need way more activity put into them. And of course, as always in high energy physics, the accelerator deadline is there to keep your feet on the ground. And I should say that this project, I think, which is now called a collaboration. At that time, it was called a project. But this collaboration, I think it really worked as a collaboration. Everyone, there's so many people around the world, so many, who are contributing very, very positively to this. In fact, the problem really is that for me just now is that there are so many people that I can't mention them by name, unfortunately, but there are so many people who made very important contributions to this in all sorts of different ways. Thank you.
Thank you so much. Both speakers, contentful slides and very clear presentations. It was really wonderful. Thank you so much, both of you. Would people like to make comments, questions to the speakers? Such an opportunity. Thank you. It's really very nice. If anybody would like to raise hands, I'm looking at the participants list. So Gita Rachel, please.
Yes. Hi, I'm Rita Rachel from CCIN 2P3. I had a question because you said in the beginning we were the only ones to begin this kind of distributed data management and computing. While we were putting in place this model of Monarch and made it work, what was the status in the private companies and outside the world of high energy physics? Thank you.
Thank you, Gita. We don't see your face, but it doesn't matter.
Oh, okay.
No, we don't see Gita's face.
Ah,
We see
okay.
less.
I put it. I'm sorry. I put it, but okay, I will do it.
Now it's better. Thank you.
Because I was on the wrong monitor. Sorry.
Okay.
So please,
I think
less.
I mean, at that time in 1997, 98, and even in 2000, there wasn't really any commercial activity in this area. There were lots of other sciences who were looking at this, and I think that probably most of them were using the Globus toolkit. But I don't know if that was the case. I mean, probably the only ones that we were really hearing about were using it. I don't, but there certainly wasn't a commercial thing. I mean, now if you're thinking in terms of clouds, I said at the beginning that it was actually just about the time that we were coming online with LHC that the first cloud, that you might call it a cloud, is the Amazon Web Services. They produced these two products for storage, simple storage service and their Elastic Cloud. So this was just beginning. Now that of course grew then dramatically and it's become very competitive, but it's not exactly the same as the grid. I mean, the cloud is a bit the other way around. It's more, you have a gigantic computing system, usually in one place, and you have virtual clusters which are carved out of it. And whereas our the goal of the grid was to enable you to put together, to look like a virtual system, put together geographically distributed centers. Now, whether that was a wise idea or not, I don't know. It was the only idea which was thought to be feasible at the time, because remember that we were working, the experiments were working with funding agencies who'd put an enormous amount of money into building the machine and into building the detectors. And so the idea that they would get together an enormous pack of money and put it at CERN for a computer center, which didn't have to be at CERN or somewhere else, but wherever else it was put, it's not obvious that country A would want to put their money into country B. And we had to get going immediately and get this started. So the practical solution was, everybody goes out and sees what capacity they can get, and they install it in their computer center. Maybe they add it to facilities that are already running. Maybe they set up a new cluster, but everybody goes out and does their best to collect it. And we will try to build an infrastructure on which can tie all this together and make it look like a single computing service, or sort of like a single computing service, I should say.
Thank you, and it was very successful. Given the result went out very quickly at the LHC era. Thank you.
Thank you both. Any other comment or question? I have a question, comment, slash. There were many. I was involved in this project, the GRID project, in the VO, virtual organization registration, and the certificates. And I was wondering if you have an opinion, mostly less, the health grid and the biomed and the astrophysics grid, etc. All of those that were presented as the, you know, the virtual organizations that would participate in addition to the LHC grid. Were they successful enough?
I don't know. Perhaps Frederick knows more about that, since he was deeply involved in EGE, and I don't know to what extent these became more than just pilots.
Yeah, I don't know if you remember, Les only was involved until 2005 or so, for the deeply. I share the same impression than you. There has been computing successes with health, but not necessarily based on grid, although this has certainly served them as experience. And in particular for what concerns authentication, Maria, which is a very difficult problem in terms of health. So certainly when we talk about data coming from the hospitals, as you know, hospitals do not want their data to go away and are not very keen in sharing anything for obvious reasons.
Exactly. This is why I'm asking this, because at the time I was responsible, together with Ian Nilsson, who left now, for the certification and for ensuring that the authorization in the virtual organization is done according to groups and roles in VOMS for the virtual organization management system. And this did not really work as adamantly as it was promised. And now we are trying to solve this in the SOLID project, the social link data that I touched upon very lightly yesterday with Tim Berners-Lee, where medical data are supposed to be only given to authorized people with consent from the person who owns the data themselves. But all of these efforts, you know, they are having difficulty to take off somehow.
Now, I see Bob Jones is connected. Now, he would certainly know the answer to the question of what other grids were actually led to something more than pilots.
Hi, Les.
Hi.
Yeah, so there was a number of regional grid projects that were operating during this period as well. And they did continue to develop. I think in particular, Southeast Europe is one of the important regions that has developed further. And they have continued to grow and operate. But remember as well, there was a transition at the end of the series of the EGE project. So you covered up until 2010. And then of course at 2010, that's when the responsibility from the European point of view for much of these things moved to the newly formed EGI organization that was established in Amsterdam.
Yes.
And since then, they've continued working and evolving the grid technology. And it's been operating beyond physics with many other disciplines. And we see that there's still some fruit of that happening today when we see some of the science cluster projects, things like ESCAPE with astronomy, astroparticle physics and so on. but also the life sciences, environmental sciences, and also fusion science as well. So it has continued to grow.
Thank you. Thank you. Bibo, you wanted to say something.
I have a question. I have a question for Les. Les was making the distinction between cloud computing and grid computing. I'm also curious how he thinks possibly the architecture of the grid was influenced by the web.
Well, I could have mentioned, in fact, when describing the big point of moving, from this hierarchical structure that we thought would be necessary because we lacked the software to do something better, when that morphed into a grid during the Monarch discussions. Now the grid actually is really a web. I mean, if you want to compare a grid with the cloud, the grid is a web. It just has nodes on it, which are computing and storage management nodes, rather than maybe information provided. But I'm not sure that what the web is now, because the web is many things now. So the difference is probably, it's probably not very much. But it certainly has got much more to do with the web than with the cloud, I think.
In fact, I remember presentations for the grand public where the logo or the header was what the web was for the 90s. The grid will be for the year 2000 or something, for the years after 2000. Yeah. So an association was made from the beginning, Bibo. So if we don't have anything else right now, I suggest we thank the speakers very much for these so useful and clear presentations, so well prepared. Les, if you want to resend me your slides, I'm happy to replace the ones uploaded. People in the audience are already asking. Looking forward to see you again in other contexts and other lecture series. Thank you very much. Thank you.
Thank you.
Thanks to Marcus for the links in the chat. I'm going to put them in the Indico event as contributed material during the talk. Thank you all.
Thank you.
Thank you, Maria.
Thank you, guys.
Thanks to all the speakers.
Bye-bye.